Welcome guys. So in this video, let's talk about characteristic roots. Okay, so what I intending to say is that yeah, so this is our topic today. Yeah, so I think for the linear algebra, the idea is that we are studying the linear transformation, right? So one can define AV to be a form of VV, basically, or linear transformation from V to V. So idea I mean, if you are only an undergraduate, that you will think that LV is just a vector space with a dimensional n square. So this is just view this as a vector space, right? But I said last time that you can, given any T1 and T2, right, you can do a composition, right? So this makes a V as a associative ring, right? Yeah, so usually ring should be associative, so we call ring, and also with identity. Okay, but now need that we can still times f any element in f, right? So we can talk about alpha t1 t2. The alpha t1 is still another element in it, right? So you can check its property. So this which makes this LV algebra. Okay, so the idea is that A in the finite dimensional vector space, this LV is finite dimensional is also algebra. So one can use the polynomial idea. So you can from here thinking about a so-called minimum polynomial. Okay, so this is why in the linear algebra that somehow the minimum polynomial, the appearance of minimum polynomial is not very natural, because if you don't have this property, then you suddenly talk about minimum polynomial in the only a vector space. Content is not common. It's not natural, right? But once you start from vector space, go to a ring, and then go to algebra, and everything looks natural. Okay. Okay, so now we can talk about characteristic roots. Okay, and also remember that I talked about what's so-called singular, right? So the singular and also regular, right? So when any element is a singular, means that's not regular. Regular means that the infinite dimensional case means that you can find another u in the LV such that u tu is ut equals to 1. Okay, so from here that I hope to let you guys feel that I'm talking about general objects from V to V. So up to here that we don't use a specific basis. So this tier and U are abstract objects, not the matrix itself, right? Okay, so characteristic rules. So definition. So if given t is a V, and the lambda is a characteristic roots. It's characteristics of t if t minus lambda is singular. Okay. T minus lambda means t minus lambda times identity element. If you because we don't talk about matrix, so you can still you can just write t minus lambda. Okay, so theorem before, since we're talking about if any matrix, if any element is singular, it means that you can find another vector which is non-zero, which but the t minus lambda v is 0. Right, so theorem tests that if only if there exists the v is non-zero, such that tv is lambda v. Okay, so this is a common notation. Okay. Okay, so lemma. So remember that in the previously we talked about the polynomial, right? So let's see. So the lemma says lambda belongs to. So it's not guaranteed that your lambda will belongs to your field f, right? So for example, if you only talk about a field into rationals, sorry, into real numbers, then you're in the matrix theory, your eigenvalue can be complex, right? So we need to make an assumption that if lambda belongs to field f, and they will take t belongs to LV. So this lambda is a characteristic of t. Then for any polynomial q of x belongs to f bracket x, then the q of lambda is a characteristic roots, of q of t. Okay, so this is trivial, right? So proof. So if TV is lambda v, obviously TKV is basically lambda KV, right? So combine all this, you get the Q of TV. So Q of TV is any polynomial, is basically Q of lambda v, right? So which Q of lambda is basically the characteristic root of Q of t. So you should view this Q of t as a polynomial of t. Okay, so as I say, once you admit the of t of v is algebra, then the polynomial of t looks natural. Okay, so theorem. If lambda belongs to f and t belongs to LV, and lambda is a root, then I should say then lambda is a root of a minimum polynomial of t, minimum poly of t. Okay, so minimum polynomial means that the smallest degree polynomial such that Q of t is 0, right? And the existence of minimum polynomial is guaranteed that when V is a finite dimensional vector space, since LV is a finite dimensional vector space. Okay, so yeah, so I should say in next all the section, our vector space always be finite dimensional. Okay, so lambda is the roots of minimum polynomial. Okay. Okay, and also in particular, the number of the characteristic roots of t is finite. Okay, this is simple because the minimum polynomial degree of t, minimum polynomial t is always finite. Okay, so yeah, so once we prove it, then we will have this result. Okay, so yeah, so the proof, I think the proof should be simple, right? So the proof is that suppose your p of x is a minimum polynomial t, meaning poly of t, and then we know that p of t is 0, right? And then we know lambdas belong to field f, right? So and we know that there is a v non-zero such that lambda v tv is lambda v, right? Okay, so from here, previous result tell me that the PTV is also lambda p of lambda v, right? But it's 0. Okay, but v of lambda is a constant, v is a vector, right? So we tell you that p of lambda is 0. Okay. Yeah, that's it, right? So we prove that this lambda is the root of minimum polynomial, right? And the minimum polynomial is always finite, so finite degree. So in the field F, you only always have a finite number. Okay, another lemma. So this lemma is should be trivial, so I don't want to prove. So if TS belongs to LV, then if S is regular, okay, so regular, then T and ST as inverse has the same minimum polynomial. Okay, so I don't want to prove. This is simple, so you should view as an exercise. Okay, so V is called a characteristic vector. Okay, so up to now, I may so-called call it eigenvector. I think eigenvector is like the from Germany or something. Okay. So final theorem. So this section should be simple. Right? This yeah, final theorem says that if lambda I, let's say I from 1 to k, are distinct, so they are not the same. And also O in F, and they are the roots, so they are characteristic roots of our T belongs to LV. Then the eigenvector, right, let's say V1, V2 up to Vk are linear independent. Okay. Okay, so this is the results that I think everybody knows about it. So quickly proof. Yeah, let's see. So we need to prove that this is linear independent, right? So suppose we need to show that show that what. Okay. So if so let's make a result. So we need to prove what? We need to prove that if I get alpha I from 1 to 0 I from 1 to k is 0, right? And I hope to prove that all the alpha I is 0, right, for every I. Okay. So now if somebody give me this type of relation, then I can first delete everything that already already 0 in I can delete everything which alpha I 0, right? So finally I can assure that my relation is like a beta 1 v1 beta to v2 such that beta k vk equals 0, such that every let's maybe use beta m and all the beta 1 beta 2 up to beta n all of them are non-zero. Okay. And I need to so for example, if v2 is 0, then I should delete v2 and view the v3 as v2, so I can reassemble, okay, such that every coefficient should be non-zero. Okay. Okay, so now that everything is trivial, right? We just act on t, so we get beta 1, right? So if I work on t, we get beta 1 lambda 1 v1. Right, and so beta 1 lambda 1 v1 beta 2 lambda 1 v2 up to beta m lambda sorry, so let me see. Oh, sorry about this. Okay, so let me start. So now you first have it, right? So I first apply t, right? I can apply t. So from here we get beta 1 lambda 1 v1 plus beta 2 lambda 2 v2, right? Because all the beta eigenvector, and so we get the beta m lambda m vm. Okay, but from this original equation, right, we can times lambda 1, so we get beta 1 lambda 1 v1 plus beta 1 lambda 1 v2 up to beta m lambda 1 vm is 0. Okay, this is 1. Okay, so we use these two minus, right? So we cancel this out, we get beta 2 beta 1. Sorry, this is beta 2. So we get beta 2 lambda 2 minus lambda 1 v1 up to v2 up to beta m lambda 1 minus lambda so lambda m minus lambda 1 vm 0. Okay, so this is our result, right? Okay, so yeah, so now you think, oh, this is hard to proceed now, right? But remember that in my previous proof, sorry, in my previous process, I can create. So since I only have finite dimension, right? So I can create such relation. So the idea is that I want to create such relation. What kind of relation? This relation means that all the beta 1 v1 plus beta 2 v2 up to beta vm equals 0, and all are non-zero for the smallest m. Right? Because I only have finite vectors, right? So I can find the smallest. I can, if they are not linearly independent, I can find the smallest m such that all of the coefficient is non-zero, right? But the problem is that if I get such m, then from these operations I get m. I will get another relation which only contains m minus 1 term, right? Because I only cancel, right? But this is a contradiction, right? So it means there's no kind of this relation exists. So it means it must be linear independent. Okay, so this is somehow like the mathematical induction, right? By changing to the proof of contradiction. Okay, so final two corollary. Okay, so this corollary tell us that if T is a linear transformation and the dimension of V is n, then T has at most. So T has at most. Okay, at most n eigenvalue. Okay, eigenvalues. Okay, so this is Okay, so this is the strange results that the proof direction is different from your linear algebra, right? So in the linear algebra, usually in the linear algebra, that you already write T as a matrix, right? So you will solve the determinant of T minus lambda I0, right? So then you will say that, oh, because there's this is n roots, sorry, the degree n polynomial, so at most has n roots, right? But now the proof is somehow like go the other way, right? Because we prove that if you have a distinct eigenvalues, and somehow like your vector will be linear independent. But the problem is that if you have undistinct eigenvalues, then yeah, I mean, in the vectors where you at most have undistinct eigenvalues, which you prove that you at most have undistinct linear independent eigenvectors, so it's guaranteed that you at most have undistinct eigenvalues. Right? So I should say I should either or at most have distinct. Okay. Okay. So this is okay. Another corollary. Another corollary is that if T belongs to LV and dimension V is n, and if T has distinct eigenvalues, then all the eigenvectors, right? So simply, since all the eigenvectors are linear independent, they are n of length, so all the eigenvectors span will be the whole vector space. Okay, so now span, right? So undistinct eigenvalues span will be all the eigenvectors span will be all the vector space, because they're all linear independent and the dimension is right. So should be trivial. Okay, so next time we talk about matrix and go to the difficult part. See you guys next video.